Okay, hello. So our second talk of the afternoon, we are welcoming Professor Timothy Sumner from Imperial College London. His talk will be A Universe Dominated by Dark Energy. Now the question mark.
Right. Okay, thank you. Thank you for the invitation. So I'm actually embarking upon a talk in dark energy when people may more usually have seen me talking about dark matter. But because I am an experimental physicist, and I think it's important to understand, the background of people, because that determines their perspective as to as to their thoughts on a particular problem. So I am going to give you a very short couple of slides just to give you my background, so that you can form your own opinion about whether you believe me or not. And before I go on with the question to what dark energy is. So I'm an experimental physicist. At the time I started on my career, i.e. when I started my PhD, supersymmetry, which is one of the frameworks within which you can get additional particles within the particle physics theories that you heard about just now, involving the weak interaction. So supersymmetry had already been formulated, and what at that time was beginning to be called missing matter was just sort of showing up in a more serious way than it had done before. So when I started, the dark matter problem wasn't clearly there, but it was sort of on its way. And my own sort of motivation, my experimental program, has always been heavily influenced by trying to do things that were relevant to cosmology and dark matter as things progressed. And dark energy, of course, one didn't come to the realization that was needed until a little bit later, but I'll explain that later on. And somewhat later, again, we got the consolidated models of the universe, of course with a capital U, of course, followed with which had both dark matter and dark energy as integrated components. So that's the supersymmetry bit for that, and then the missing matter issue was coming up primarily at that point in time in relation to the galaxy rotation curves, which you've just heard about. So what have I been doing? Well, I started in about 74, working on the neutron electric dipole moment, and the relation there to the topic of this meeting is that it relates to supersymmetry, and also to axions, which are another candidate particle that are out there, which could be dark matter. And the photograph I've chosen to illustrate that actually shows my old supervisor, where we were putting together some of the apparatus needed for that experiment in Grenoble. The second thing here is Rosetta, X-ray satellite, and that has a connection through the fact that some of the X-ray observations done by Rosetta actually are among the key observational things that pointed out to dark matter, the need for dark matter. Then we have 1987, this is now a satellite experiment called STEP, which was aiming to do a very high precision test of the equivalence principle. This is a universality of free fall. And that actually has a very serious connection to general relativity, to Einstein's general relativity, because the equivalence principle, or if you like, the universality of free fall, is the very foundation stone on which Einstein built general relativity, with no justification other than that was what the experiment seemed to be showing. And so there are still experiments going on the equivalence principle, and STEP was one that we followed on this time frame, trying to do an experiment in space. We also, as a sideline, developed a proposal for an experiment to go on that same satellite, which could have detected axions. So you can see, and now, oops, yeah, I'm going ahead of myself. So that's STEP. Then we have the direct dark matter searches, and I've been involved in quite a number of those. One in the UK here called Zeppelin, was done in a deep salt mine up in Yorkshire. And then Lux that you heard about just now, and Lux Zeppelin, so that's those now being done in the US. And gravitational waves since 1995. I've been involved in the LISA Pathfinder project and LISA, where there is relevance to dark matter and dark energy, and you've heard references to those in the last couple of talks. And finally, one of the things that came out of this aborted effort, so there's Lisa Pathfinder and there's Lisa. I will talk a little bit about Lisa later on. But one of the things that came out of the STEP effort was that an offshoot of that did actually get done by the French Space Agency, CNES, called Microscope. And that actually published, we published at the end of last year, what is now the world's best sensitivity test of the equivalence principle, getting to 100 million parts to one that the equivalence principle is valid. So, and that was done in space. So that's the sort of things that I've been doing. So that sort of sets, you know, my background in terms of what I'm going to now say. So I'm going to turn now to the changing concept of our universe. You've heard some of this already, which is a good thing actually, because you heard about this part of it from the talk before last, so I don't need to cover that again. I wasn't intending to anyway. But I was really wanting to start at Newton's law of gravity, which came out in 1686. So there's Newton. And his formulation of the law of gravity was that there exist forces between any two masses, which is actually generated by the masses themselves and is proportional to their product and depends on the distance, 1 upon the distance squared between them. So that was the basic law of gravity that he came up with and formulated in terms of a real force between these bodies, and that was very successful, or is very successful in explaining the solar system and many other objects where it is a relevant application. But then in 1915, as we heard earlier, Einstein produced his different view of gravity, which is a very different concept altogether, where what is happening is that the presence of mass and energy within the universe is actually distorting the very fabric of space-time. So that's sort of depicted here, where you have a very massive object which is actually distorting the sort of fabric of space-time in which it is sitting. And if you then look at the path that another smaller object takes in its vicinity, as far as that particle is concerned, it's still following a straight line. It just so happens that because the distortion in the space-time continuum is that its straight line path actually takes it on what appears to be a curved path around the object. So that's a very different formulation to Newton's one, and we no longer talk about it as a force. It's more a distortion of space-time through which objects then have to find their way in what to them are straight line paths. So that was 1915, and that was a law of gravity, a reformulation of the law of gravity. Then in about 1917, Einstein was obviously thinking about how that law can be applied to the universe as a whole, because after all, the universe is just another system of objects that will have gravity acting between them, and one should be able to come up with a formulation that can describe the whole universe. And in doing that, he added this extra term in here, which will the role of that will become apparent a bit later, but essentially it's something that goes in there to act in the opposite sense to what gravity does, because gravity can only pull things together, and maybe you need something else that can sort of resist that. Then there were a number of early sort of works which were looking at the formulation that Einstein came up with and trying to solve the equations, to try and find solutions to the universe, starting with a static solution in 17 from De Sitter. And then Friedman, 1922, came up with a solution where the size was able to be time dependent, a dynamic solution. And the first one that's acknowledged as being a well-founded expanding universe solution came in 1927 from Lemaitre. And then in the years following that, there were a number of collaborative works between combinations of these people that came up with different solutions. And a rather early sort of compilation of those of what those models, how those models worked, is shown here, where we've got time along this axis and the size of the universe going upwards. So as you go up here, the universe is expanding. If you follow this curve here, at some point it comes to a halt when the expansion stops, because gravity sort of has got hold of everything and has stopped it expanding. And it then, under gravity, starts to collapse again. That's a particular solution there. And then there are other solutions. There's one here, for example, where one has this curve here that goes over here. It's listed as marginally open. There's a situation where it could sort of gradually coast up and actually stop expanding, but not collapse again. And then there are even solutions where it can do rather strange things, starting an expansion and then halting for a little while and then starting off again. So these were rather early concepts, all theoretically based. So then, of course, what the situation needed then was some experimental data to try and hinge some of those theoretical possibilities. And in 1929, we had some observational data from Hubble, which was actually plotting by looking at you've heard this before, by looking at the spectrum, you can actually get, by looking at the detail of the atomic lines, you can get velocities out of the data. By looking at the velocity seen in the experimental data and looking at how that depended on the distance that the object was away from the observer, it appeared as though there was a correlation here that was at a positive slope. I.e., as you were going further away from our observational position, things were actually moving more quickly. And that is one characteristic of an expanding universe. So that was 1929. And this is just a replot of some of the previous one, but for some generic cases. So you have what's called a closed universe here, a flat universe where it goes where it coasts to a sort of a standstill, and then an open universe where the expansion just goes on continuously. And you'll notice that on both those plots there's a line on there which is sort of labelled now, which is the where we think we are on these curves at this point in time, where so this is the past universal behaviour, and this is what will happen in the future. Okay, so that was the first evidence, the serious evidence for an expanding universe in 1932. So then other things that have happened, as you just heard, has been the quest for dark matter. And observationally, in terms of sort of modern-ish astronomy, I put the start of that around in 1932 with Oort and also with Zwicky. Oort was looking at stars in our local neighbourhood, how they're constrained by the gravitational pull of our own galaxy, disk of our galaxy. Zwicky was looking at clusters of galaxies and how they hold together as ensembles of collections of galaxies. Rubin then is the main person thought of when you think of rotation curves of galaxies. So all that evidence was building between 32 and 75-ish, gradually building up the case for dark matter, and this is when I started on my career in this sort of just towards the end of this period. Then there was another thing happened that in round about in 79, Guth came. One of the things that had been bothering people about the universe for quite a while were a number of problems. One called the horizon problem, which is when you look at what the size of the universe appears to be today, and you think how old it is, you sort of come to the conclusion that there are parts of the universe that are so far apart they could never have been connected by any information transfer, because the size is larger than you could cover. The distance is larger than you could cover given the speed of light and the age of the universe. So that was called the horizon problem. Another one was the flatness problem, because by this time the implication of the dark matter situation was that we were getting towards a situation where we had what was thought of as a flat universe, and one often talks about that as having a value of omega, which is the matter density equal to 1. And a number of people were saying, why is that the case? Why should it be so near to this critical value? It just seems too much of a coincidence that we're that close to this critical value. And so those were the two main things, I guess. And one of the theories that came up was, well, we can get over this horizon problem by saying that instead of the universe just having expanded gradually, from a point, it actually goes with a big bang to start with, and it inflates very quickly, so that points that end up a long distance apart were actually in communication when it was much smaller. That's called the inflation, or the theory of inflation, came from Guth in '79. And one of the things that came out of that is that theory and most theories of inflation that followed naturally had the requirement that omega is equal to 1. So that sort of was one of the motivations for that. And all this evidence coming together was 1982, and there were 3 groups who sort of came up with the cold dark matter paradigm, which sort of then formed the basis for the dark matter going into the universe as such. But there was lots of other observational evidence from X-rays from clusters, gravitational lensing that was asked about just now, N-body simulations, and to some extent the CMB at that point. And I sort of collected these together in this view graph. And that move is not working. Oh, I don't have time to do that. This is meant to be a movie that shows one of the very early N-body simulations where one had to put the dark matter in to get the simulations to produce structure on the required time frame that correspond to what we think we see. And so one had this pie chart that you've seen earlier on where the consensus was building that this was the sort of percentages of the universe as deduced at that point in time, with this 63% dark matter and the rest what we know about. And so one then had this picture of the universe that you've seen all of this diagram before, but I'm just showing a part of it now, where you have this creation point at the beginning, which may or may not have been a quantum fluctuation out of an empty vacuum. That's one of the suggestions. And the rapid inflation that then occurs lasts for a tiny fraction of a second. Over the next 3 minutes, you get all the lightest elements of the being generated in the first 3 minutes. Tiny little portion on top here. But it is the nuclei, and along with those, there are free electrons, and they prevent the universe from being transparent at that point in time, because the photons keep scattering off them and can't escape. And then at this point in time, 375,000 years afterwards, the nuclei and the electrons get together to form atoms of hydrogen, and at that point the universe becomes transparent, and then the cosmic microwave background that you've heard about previously is actually the image that then was able to escape, if you like, from the universe at that point that is seen in the. So when you look at the CMB maps, what you're looking at is an image of the universe as it was at 375,000 years old. And then, of course, from that point onwards, the only thing that we know about that's going to start to then meld that universe and build the structures that we see today is gravity. And so gravity from that point on takes over, and the gravity has to mainly come from dark matter to cause the small structures here to grow into large enough things to become galaxies and clusters of galaxies and whatever on the right time frame. So that's the first part of the universe, the unknown universe, if you like. 1979 we now move to, when 2 groups, Perlmutter's group and Smith and Rees, about the same time frame, were looking at type 1 supernovae as standard candles. So these are explosions of stars into supernovae, but they happen in a scenario where you, because of the formation scenario, you expect exactly the same thing to happen every time they go off. And so you can use them as standard candles. And they were looking at how bright they appeared, which is on this axis here, as a function of how far away they were through the universe. And apologies, you probably can't, but the model curve that was expected to be followed roughly at that point in time was this 1-1 curve here, which is actually this one here. So the second solid curve up is the one that was the expectation. what was actually seen when they plotted the brightness as a function of distance was that that was fine down here at low redshifts, but then as you got to further and further away, the points are all systematically above this line. And what that means is, and unfortunately, this scale is such that as you go up, they're getting dimmer. Well, you can sort of deduce that from the fact that if you go further away, they're dimmer. But these are more dim than you would expect them to be from what was at that point the standard cosmology, just containing dark matter. So how do you make them get further away? Well, you have to have something in the universe pushing them further away. And that was then the birth, if you like, of putting in the dark energy. And using their data, they could make a plot of the amount of matter compared with the amount of dark energy. And the data that they got sort of indicated that the real answer was somewhere within this uncertainty area here. And the expectation for a flat universe, although the definition is now slightly different, is that if you have a flat universe, you'd be somewhere along this line. And so there's sort of a focus on this region, but you know, I mean, the data were just saying it could be anywhere there. Nowadays, we have, or rather not nowadays, but 4 or 5 years later, one also had the information from the WMAP satellite, and I'll show you some from data of that sort in a minute, plus information from looking at extensive surveys of galaxy distributions throughout the universe, or throughout the observable universe at that point. And here you can see the constraint that is from this one. And the neat thing is that when you build in the evidence from other types of observations, like the cosmic microwave background, and how those tiny seeds of inhomogeneity grow into larger structures, and then you build in the information from clusters, which is how it all arranges itself into formations within the universe once it's grown, they tend to delineate regions in different directions, which is very good, because then you know that to get consistency, you really have to look at the intersection point of all of them at the same time, and that's where your answer is most likely to be. And if you just track across to the side here, you can now see, well, it's less than 1, but it's more than a half, just by eye. And you can go down here and you can say, well, the dark matter, roughly about 0.3, just by eye. And then this little red line here, there's been a question about how do we know, how can we be sure that what we know about all the normal matter, as it were, how do we know it's only 5%? That's sort of delineated by this solid line here. And one of the main arguments used at this point in time was that our understanding of how these lighter elements formed in the early universe was actually thought to be pretty good, or is thought to be pretty good. And if you mess around with this too much, you destroy the consistency of that theory, which that's just another piece of it. So there's lots of bits of evidence that all go together to give a consensus of where things are. Now, I tried to think about how to illustrate dark energy. So I came across this little gas simulation, an educational tool. So think of this yellow area as the universe. The number here is the energy, the dark energy, if you like, in that universe. The bluish barrette thing on the top here is what's holding that gas in the box. So that's the dark matter that's providing the gravity that's pulling it all down. At some point in time, what I've done in this simulation is I've increased the amount of energy, dark energy in the box. You'll notice here there's a measure of temperature, which is really a measure of how fast these particles are moving around. And of course, in this particular situation, there you can see the dark energy has changed. The volume of the box is now going out. So that addition of dark energy is expanding that volume. And of course, the pressure that's being applied on the bottom of this dark matter slab here is from the molecules bouncing off the bottom of the thing here. At some point, a bit later on, I hope not too long, you'll see this blue band gets thicker, because I've then at that point in the simulation I've added more dark matter into this analog of the situation. And you'll see that visually, because this will just get fat. There it goes. So the energy is still changed at the higher value that I inputted there, but you can now see the volume is now decreasing again. So that's the universe now decreasing in size because the dark matter's become more dominant. And just to then cap it off, leaving the dark matter as it is, this energy will now go back down to its original starting point. And what you then expect is this to collapse even further than it was at its original positioning, which you can, if I went back to the beginning, you'd see that's the case, but I don't have time to go back and show you that. So that's the best I could get to as an analogue of it, trying to explain what the effect of dark energy is and what the effect of dark matter is. Because quite often it's confusing that, when Einstein has this equivalence between mass and energy, so why if you add energy, isn't that the same as adding mass? Well, I've tried to illustrate that there. Okay, so where are we? What is the current state of play with this? Well, there's been a satellite called the Planck Satellite, a European Space Agency satellite, which has now produced the best results so far. The original results came out of the US WMAP satellite. These are now the Planck Satellite. And you can see their publication in July 2018. And that just shows you you can get a feel for the number of people that get involved in these types of project. And this is just one of their papers entitled Cosmological Parameters. There's a map, and there's an illustration of the satellite. And there's the abstract. So if I leave you to read that for a while. But let me pull out the key things. So the first thing is we find good consistency within the standard spatially flat 6-dimensional parameter lambda CDM. So lambda CDM is now cold dark matter plus a lambda contribution, cosmology. That's scientific speak for it works. And they then, within their 6-parameter model, 2 of the parameters relate to density. One is the dark matter density, which is the cold dark matter density here, which is, don't bother about the h squared there, just look at the number, 0.12. And then the baryon density, which is everything we already know about, that's 0.02. So you can see there's a factor of 6 difference between those two. And then look at the uncertainty here. This is 1 part in 100. So if you get an 100, that's 1 part in 100. Each of these numbers is known to roughly. So there's a factor of 6 difference between them, but individually those numbers are very tightly constrained. And then if you put those 2 numbers together with the assumption, and it is an assumption at this point that we're in a flat universe so that the addition should be equal to 1, then you take these 2, add them together, take them away from 1, and you end up with 0.6847. So that's the 68%, and that one, because this one hasn't got the h squared in it, but that's where the 68% dark energy comes from. That type of calculation. And in terms of, if you look at this plot here, this is then showing you the matter density, the total matter density here, and it's showing you how the estimate of what the number is gradually improves as you sort of add the different bits of information that are coming from the data together until you get to this darker blue box here, and that then is what we call the uncertainty box, where the number, that's what determines the 0.001 here is the width of that box. Now I'm showing you this, you mentioned one of the questions said, I think it was sort of saying, why do we believe in dark matter and dark energy, essentially. And I think the answer to me is that when you have a model, which is the solid line here, which fits data to this level of precision, and it's actually fitting a distribution of points which is non-trivial. It's not as if it's just fitting a gentle curve or something. It's fitting a curve with quite a distinctive sort of shape with a number of peaks in it. There's actually 7 peaks in this. And it's fitting it with such a level of precision. You think to yourself, well, there's got to be something in this. Okay, there's 6 parameters in the model, and there's 7 peaks, so some people may raise an eyebrow at that, but just look at the sort of features in that data and how well the data are fitting the model. And not only that, if you then say, well, what does that model imply for other things that you can observe, and there's a list here of all the other things you can observe. One of those you'll notice is type 1a supernovae, which is where the first indication came from, but there's now several other types of observation which all give you information on dark energy. So not only is this data consistent with your 6-parameter model, it's also consistent with all of the bits of observation that come out in those different regimes as well. That's getting pretty convincing. And that fit requires dark matter and dark energy down at this percent level that I just showed you. So one now has this current sort of best pie chart here with almost 70%, 27% of dark matter, and then this 4 or 5% of ordinary matter. Okay, I think I probably need to move on. So now I can reveal the second half of this plot that, of course, you'd already seen. And the point to notice now is that instead of this sort of, diameter remaining flat, it now starts to splay out at the end, and this is the effect of the dark energy. So let's talk about the explanations, possible explanations. So I've just got a summary here, a recovery here of dark matter possibilities. You've seen this already, so I don't think I'll say any more to this, other than new particles, modified gravity are the two issues there, the two suggestions there that still remain serious suggestions at some level of credibility. And then we have, what about dark energy? That's really difficult for me to cover that in any great detail. So I thought, well, I'll just have a look back at what Planck said, the Planck Consortium said about this in 2015, because that's the last publication of theirs which looked at the implications. And you find this statement: there appears to be a vast array of possibilities in the literature. No agreement yet in the scientific community on a comprehensive framework for discussing the landscape of models. Oh dear. So then I thought, well, maybe I can find a good presentation that somebody else has given very recently to see what they say. And I found this one, which is a really nice, and there's a statement: more than 10,000 papers on different explanations models for dark energy. So I thought, well, I'll do what this guy's done. And I think it's a sensible thing. Here's just to give you a flavour. If you look at what the Planck Consortium did in the end, they did look at a number of models. So this is a number of models that they felt they could understand and justifiably confront with the data. Some of those were dark energy fluids, actually dark energy getting into the system one way or the other. And a number of them were modifying gravity, modifying GR. And then there's another paper doing a similar thing, and you can see a number of lists of names, and you can see names that you may have heard about, like quintessence and k-essence and other things coming up there. But in the remaining time I've got, of course, it's completely impossible for me to do any real justice to that, but I think it's instructive to look at the most simple thing you can think about, which is a fluid model, where you just relate the pressure to the density in the fluid by this with a parameter omega, and you can think of that can be connected to a cosmological constant if omega is -1. And you heard earlier on about the relative importance of dark energy versus dark matter, and that's illustrated in this plot here. One of the strange characteristics of the dark energy implemented as though it were a cosmological constant, as Einstein had originally proposed it, is that it would actually be a constant over the lifetime of the universe. So it would sort of sit at some level. This is then energy density here. So it sits at some level of energy density and just stays there. Whereas the density in the matter and the radiation, the energy density in those two, drops as the universe expands because it becomes more dilute. So although dark energy would have been subdominant in the early universe, as you heard earlier on, it becomes more and more dominant as we go through the current era, to the point where it actually, the other energy densities have dropped below it, and it now becomes the dominant thing, and so that then takes over and is able to overcome the decelerating effect of dark matter. So that's one sort of scenario that one can explore in a rather general way. And then you can just make it a little bit more complicated and say, well, let's not keep it as a constant, let's let it vary, and we'll assume it varies in some in some way that we can apply analysis to. So think of A here as being a placeholder for time. So you've got a basic value, but then it varies away from that as time goes on. So let's look at Planck first. So what does Planck say about these particular situations? So what is on this plot is omega naught and omega A. If omega is -1, of course omega A is 0, and omega naught is -1, if it's a constant. So here's the plot. Omega naught is here. There's omega naught -1. There's omega A equals 0. And here are the constraints that Planck has already set on that type of model with the data they've got. Actually, this was as of 2015. I haven't seen the latest one from the... it's not been published yet. But as of that point, the uncertainty box is certainly encompassing the -1, 0 data point. If you then look beyond a cosmological constant model to other types of model, you can find generic sort of regions where they may sit in the omega naught, omega A plot. And this is just one compilation taken from De Putter and Linda in 2008. You can see again omega naught -1 is here, omega A naught there. And these other types of model actually have possible values that sit within this shaded regions. And one goes down here, one goes up there, one goes up there. Here's another variant of that from Chen and Gu, 2009, where here you can see an interesting thing where there's a region on the left of -1 where some theories sit. Again, the region going up there, down there, down there. So, okay, I'll come back to this one in a minute. So there are actually a whole host of possibilities of combinations of omega and omega A. So that's omega A, it's just different symbolism in this. So there are actually a lot of different combinations out there within different types of theory. So different theories you would think could sort of have any consequence you like almost for the universe. And this is sort of illustrated on this slide where the two extremes are a universe that expands, has a period of acceleration that just gets more and more accelerated. And that type of model has been christened the Big Rip. And then you have another model here where the combinations of omega naught and omega A have been, can be tuned such that gravity can actually get hold of it again at some point and bring it back down into what's called a big crunch. And along with the big crunch is this concept, well, maybe everything's cyclic. Again, a question that came up earlier on, that maybe you start at a bang, you have a crunch that then leads to another bang, and you get a cyclic situation, such as is shown here. So I think theoretically, it's wide open still what the fate of the universe is. So how can we try and home in on what the real situation is? Well, for dark matter, I think you heard earlier on that there are suggestions for new particles, suggestions for modified gravity. Both within those two suggestions, there are things that are clearly amenable to laboratory scale experiments that the likes of myself can actually put together, given enough money, of course, and go and try and look for these things. So with the particles, we do dark matter experiments underground, or if they happen to be weakly interactive particles, or if they're axions, we put together conversion chambers that can convert them into photons that we can see. Modified gravity, what we need to do there is to probe gravity on the right sort of scales to be able to see departures from Newtonian gravity, and there are thoughts there about, we can continue to get solar system ephemerized to better and better precision, and maybe something will show up there. Or we could even think of doing experiments, as a sort that I would like to have done with LISA Pathfinder, and actually send that through the so-called saddle point and go through a region where there may be anomalies in the way Newtonian gravity works. So one can think of doing things there. With dark energy, it's a bit more difficult, because as far as I know, there are no direct experimental tests of dark energy that one can do on a laboratory scale. So all you can do is to continue looking at the experiments that are already being done out there in the universe and study it more and more carefully to see what you find. And of course, if you do that, one of the problems you come up with here, for example, is if when more data comes in, these uncertainty box shrinks and shrinks and shrinks and shrinks, and it shrinks about this point 10, you don't differentiate between the theories because they all converge on that point anyway. So to my mind, there's somewhat of a difficulty there. But nonetheless, what you're looking at is how the universe is behaving. And there are an enormous plans for gathering more data of that type here. I've got a summary here that's come from Linda. So you can see lots and lots of things there. And Lisa, of course, you've heard earlier on, Lisa's been mentioned a couple of times. That has something to say about, or will have something to say about that when that goes up. Starts measuring the gravitational waves, the ripples in space-time, because it can do so at quite a large range of redshift with different types of object that it will see, and actually produce a similar plot, omega naught versus omega A, with similar uncertainties to Planck. Still doesn't get the final answer. And we can probe dark matter by doing the idealized experiment of looking at a little tiny black hole, stellar-sized black hole that has got itself in the vicinity of a supermassive black hole and is spiraling around in the process of being captured. And if we can get one of those, I'm going to take the time to, which way? Is it on there? All right. I want to get to that. I'm not sure I'm going to be able to. Is the pointer on the screen? Can you see it here? Yeah. Oh, so I've gone the right way. All right, okay. God, it's amazingly difficult to do things. Right. This is a soundtrack of a simulated data set for this particular type of object, and it's a simulated chain of data that's been derived from full-blown numerical relativity. So it's a serious waveform calculation. So be prepared. Sorry, that's my fault. I haven't got the sound on the machine. Never mind, I haven't got time for that. Sorry you can ask me a question afterwards if you like. I put that in just before I started the talk because the previous speaker had actually played a soundtrack from the LIGO sources, and I thought, wow, I should put one in for one of these. Okay, Lisa may well have something to say about cosmology because it will be able to access information from this era here. This is 10 to the minus 10 seconds. This is 10 to the minus 32 seconds. So it's way earlier than the microwave background here. This gives us access to information that you cannot get in any other way. So there's my last slide. Sorry, I've overrun a few seconds. Well, a few minutes. Lambda CDM cosmology has survived 20 years. That's quite a feat, actually, with such an important, and dramatic model to have come out, and it's survived 20 years with a lot of testing. WMAP and Planck have produced precision data with distinctive features which can be fitted by a flat 6-parameter universe. The universe has 2 large unexpected and unexplained parts. Our known world is only 5% of the total. Plausible explanations for dark matter and dark energy. Dark matter may see a direct resolution if one of the experiments gets lucky. Dark energy will probably only see high precision indirect narrowing of the possibilities. That's my take on it. Of course, you might say, well, Occam's razor really should favour the simplest thing you can think of. And you may have noticed that modified gravity has been mentioned as solutions within both of those regimes. And wouldn't it be consistent with this if we found one modified gravity solution that did dark matter and dark energy at the same time? I think that would have some weight. However, Occam's razor is very easy, but think of yourself being some intelligent being who happens to live in the dark sector, and you suddenly realise there's 5% of our universe we don't understand. Would you think it was as complicated as we are? I guess not. Okay.
Thank you very much. thank you very much. So, yeah, I'm sure there will be plenty of questions, but I remind you at
Oh, no.
4 o'clock we have a break.
Thank you. On the subject of modified gravitation, your colleague at Imperial, Professor Faye Dowker, is a regular guest at our local astronomical society in Crayford. And she's proposing, instead of a smooth continuum for space-time, quantized pixels.
Yeah. That's not the first time that's been suggested.
Okay, I mean, I wondered if that's a theory which is applicable to this set of problems, if it's been assessed in this way for a solution to dark energy, dark matter.
You're saying can the fact that you quantize space-time in itself solve all of these problems immediately? I suspect not, but I suspect there are twists that you can put on that may have some, that may go in the right direction, but
if there were specific boundary conditions in passing from one pixel to another, for example, then that effect would be massively magnified on a cosmological scale.
Yeah, but don't forget, it's not. I mean, you have to do one thing with the cosmology of the universe as a whole, and something else with the dynamics of the objects within the universe. So you have to do those two things at the same time if you're going to get a modified gravity that satisfies both dark matter and dark energy. I mean, okay, you could get a modified gravity that solves one or the other, and then the other one has a different solution, that's fine. But, you know, I've mentioned already there's 10,000 papers out there. You know,
could you do me a big favour? Could you possibly put up the slide again with the tabulated different variety of theories? For
but I can, but
it was about 15, 20 slides back.
All right, while I'm doing that, I'll also do this. So that if somebody asks me a question, you might get to hear the soundtrack. So there was that one. Oh, you can't see that. Oh, you can, yeah.
Yeah, no, it wasn't.
Let me, from current slide. Oops, where's it gone? There we go. So there was that one, and then there was this one. These of course, are taken from other sources. So, you know, I'm not going to stand here and defend any of these because I'm an experimentalist, and I haven't read all 10,000 theory papers. So, but yeah. Oh well.
Thank you very much. A couple of questions related to the cosmological constant, or perhaps parameter. The first one, you mentioned that in natural units it was 10 to the minus 122, and 10 to the minus 122 is an interesting small number, but one that...
I'm not sure I mentioned that, did I?
No, it was on your slide.
Well, it's on my slide, but it's probably a quote from somebody else.
Yes, which I thought was an interesting number and maybe pointed to...
Yes, okay. There is a... I don't know whether this is where your question goes, but I mean, people were hopeful in the early days that there was a natural explanation or natural candidate for lambda, in the sense that we know that within quantum mechanics we have this thing called the vacuum energy that you can't, you know, is always present. And so could this be a vacuum energy equivalent operating on the scale of the universe? But if you work out the numbers, they're disgustingly wrong. So does that mean that that's not that process? Well, it means that the way you're calculating it is not appropriate to the universe, at least. Whether it's still the basis of the explanation, I don't know. I mean,
that was really the question of whether it was a good basis or not.
Well, I mean, my gut feeling is that if you predict a number from quantum mechanics that's way too large, then that's got to be wrong anyway, because we don't see it. But it may be that you know, if you do it right, you may eventually come out with this tiny number. But of course, it's almost a fine tuning. You know, why would it be this tiny number and not zero? You know, I mean, but there's clearly scope for more thought on that, I think.
Just a general comment. If you can't see dark energy and you can't see dark matter, I'm always puzzled how physicists say that we only know 5% of the known universe.
Well, because I sort of tried to convince you of that by showing you the Planck data and how how featured the Planck data is and how well the model that we have fits the data. And so I think there's a philosophical point here, of course, because whenever you try and explain experimental data, because that's all there is really, is all you've got is experimental data, observational data. What you're doing is putting together a model that you then translate into mathematics, and you're saying this model fits those data, and as long as it's predictive, it's a useful model. But is that reality? I don't know. That's just a mathematical model we put together. So in this case, we put this model together, and our concept of how it works involves this dark energy and dark matter, and it's worked so far. So I don't think there's the model is there for what it's worth, but I don't think there's a case for dismissing it. If you don't have dark matter and dark energy, you have to do something else, because it's clearly inconsistent with the application of Newton's law in the simplest instance to galaxies and general relativity applied to the whole universe. I mean, clearly there's something not right there. So I don't know whether that answers your question, but that's my answer. That's the way I think of it.
Well, I don't know.
Yeah, okay. Oh, sorry.
Why is the gravitational and Hubble constant always changing?
Well, the Hubble constant is a measure of how fast the speed is changing as you move further away from us. And if I haven't got it there, but that plot I had showing the universe, where it's sort of expanding and then it's changing. It's really a measure of the slope, if you like, of how the diameter is changing as a function of time. So if there's a shape there that sort of, then the Hubble constant would expect to change in those different regions, I think.
The Planck curve that you just mentioned with the 7 peaks and the very, very good fit,
Yeah.
it seemed a fantastic fit on the right-hand side, but if I understood it correctly, it all went a bit wrong on the left-hand side. Is that an important part of the graph to understand, or is it irrelevant for some reason?
Oh, it's not. It's not irrelevant. So there's two things going on there. Firstly, you saw that the experimental data had larger uncertainties. Okay, and this is information on the largest scales. So as you go to the left, you're going to the larger scales. So it means that when you take the data, there's a big uncertainty in trying to get that largest scale information. But you notice that the model did actually, go through the data points. So I don't. I think it's more a question of what can you recover from the data, and when you get data, there are always fundamental uncertainties, which are not mistakes or errors. It's just that there are fundamental limitations to how accurately you can measure certain things given the data that you've got. So I think what you're seeing there is really the uncertainty bars. That most people call them error bars, but I tend not to do that because it conveys the wrong message that somebody's done something wrong. It's fundamental uncertainties in what you can recover from the data is why those bars get bigger and bigger.
Your final slide raised the idea of sapient beings in dark matter, which made me think that as a non-physicist, I tend to imagine dark matter as a kind of homogeneous soup. But maybe that's the wrong way to visualize it. Should we visualize it more clustered? And would that make a difference to how we look for it?
If you think of the talk before mine, where the main issue, the main concept being pursued there was that dark matter is in the form of particles. The size of those particles, the mass in each of those particles, could be anywhere from tiny subatomic particles up to quite large things, even dark stars. So the size of those individual objects could be, could go up to quite large values. And even the, one even hears about the LIGO black hole mergers, which are sort of 100 solar mass sort of objects, possibly being dark matter. So. Or being black holes which have a primordial origin, which would effectively be dark matter. So So there's a huge range of scales of size of object that there could be if it's in a particle form. If it's not in a particle form, you know, I mean, maybe, I'm just trying to think of an example. Axions, for example, we talk about those as a particle, but they really have a fluid type behavior. Or if you think of modifying gravity, obviously then that's a modification to the way gravity works as a function of distance. So I think there are many possibilities out there. Some of the particle possibilities are more clumpy than others because they involve particles of different sizes as their building blocks.
We hear things on the news and we don't hear a follow-up and they just disappear. Two things I've heard about was a galaxy with apparently no dark matter, implying a modified theory for a modified gravity theory wouldn't be applicable more because if you see a galaxy with no dark matter, modified gravity should work for that gravity as any other galaxy. And the other one was a particle they discovered coming up from the Earth, a high energy, it's supposed to be looking for neutrinos or cosmic rays, but it was too high energy coming up from the Earth. It might be a sterile neutrino or something, was that? But I didn't hear anything after either of those two reports.
No, I haven't. I've obviously heard of them. I haven't researched the papers myself to get a personal opinion on those. I mean, there've been lots of statements released from time to time, going back decades, about, you know, observations that tend to suggest there's a discrepancy between the paradigm and what's really there, and that creates a good deal of activity where people look into it more and more deeply, which is a good thing. And so far, those have always been resolved to the point that the paradigm still exists. So I think, you know, it's good to get these new observations coming out, because at the end of the day they have to drive how the theory develops, but one also has to be very careful in assessing critically both the credibility of the observation and the implications that it then has for the theory, because those two things can go in. So on those two particular things, I don't have a personal opinion, but I'm just saying in general that.
Thank you.
I just wanted to ask if any of the expansion of the universe beyond what was expected can be explained by variation in the speed of light over time, and how would that go?
Well, we're seeing we're currently in the period of acceleration of the universe. So I suspect the answer to that is probably not immediately relevant to the expansion of the universe, although you know, anybody who knows differently should sort of speak up. But on the other hand, it's not to say that some of the theories that are, you know, going to be producing the dark energy might not have as consequences that they may predict the varying speed of light, you know, in some form. So I doubt there's a really direct implication in the way that I think you're implying, but there may be that some theories have that as a side effect. You know, that there could be a variation to the speed of light in some circumstances.
Okay, sorry, but you can continue asking questions during the break, half an hour break. We'll be back at 4:30 for a summary of this lovely session. So thank you very much.